Okay, and so starts chapter 37, and we'll be talking about relativity. First, we're going to start with two postulates that Einstein came up with dealing with relativity and why he was interested in those. And then we're going to talk about what happens when things go really fast. And it turns out that two observers in two different reference frames can disagree on when something happens. And so as you go really fast, then time is going to start to dilate, length is going to start to dilate. We'll have to redefine what velocity means, and we'll also have to redefine relativistic mass, relativistic force, relativistic momentum, kinetic energy, and then we'll touch briefly on the just general relativity in general. Haha. Now, when we talk about relativity, we're talking about things that are traveling really fast. So 99.995% the speed of light, which may also be written as 0.99995 multiplied by c, where again, c is the ultimate speed limit of the universe, which is going to be the speed of light in a vacuum, which is going to be 3 times 10 to the 8th meters per second. And again, as I said, as we start to travel faster, we'll have to redefine time, length, mass, energy, and momentum. So let's take a step back in time, and actually not too awful long ago, it was the year 1905, when a fellow by the name of Albert Einstein came up with some really important postulates. And the first one, it's pretty simple sounding, but it actually has far-reaching implications. And his first one said that the laws of physics have got to be the same in every inertial reference frame. And what that kind of means is if we have two observers that are moving at different speeds, then the laws of physics will apply to both of those. And that's kind of important because it's saying that one reference frame won't be more right than the other reference frame. So if you were to think about if we were traveling on a train and you threw a ball up and you caught it, then gravity still applies in that reference frame just like it does if you're not moving. Another example is if you remember, if we have a magnet and we shove that into a coil of wires, we're going to induce a voltage or an EMF, and it doesn't matter whether the magnet is doing the moving or the coil is doing the moving and the magnet remains stationary. Both of those are going to induce an EMF. We're going to have the same exact result. So the laws of physics are going to work equally in both of these. Now, Einstein's first postulate leads us into his second postulate, and what he kind of says is, well, if Maxwell's equations work in all reference frames, then the speed of light has got to be the same in all reference frames, so the speed of light in a vacuum. And so what that means is the speed of light is not going to depend on the motion of the source. And if we were to, kind of think about it, if we had a spaceship, and this spaceship right over here fires a missile, then what we're going to do is we're going to say, well, if the speed of the spaceship is 1,000 meters per second and it fires a missile at 2,000 meters per second, then the speed of the missile relative to, say, something like the Earth is going to be pretty straightforward, 3,000 meters per second. This is not true about light. Light does not care whether the source is moving or not. And so if we had the same setup where we had a spaceship and it fires a light beam, we're not going to essentially add the speed of the spaceship to the speed of light. So we cannot travel faster than the speed of light. This also kind of implies implicitly that an observer will never be able to travel at the speed of light. One thing that is actually kind of nice about his second postulate is that in the year 1887, some fellows by the name of Michelson and Morley were trying to figure out what light actually traveled through, and back then people believed that it traveled through something called the ether. And what they did is they set up a Michelson interferometer, and they said we should be able to see this interferometer shifting around because Earth has some velocity, and they found that nothing shifted, and that really puzzled scientists up until the year 1905. And just a quick little post-processing note, the book has the spelling of ether wrong. Actually, it's A-E-T-H-E-R, and it was named after the Greek god of light. Now, prior to Einstein, if we wanted to talk about some physics with two different reference frames, one that is moving, one that is not moving, then what we would kind of do is we would have a reference frame, and very typically frame S is going to have an X, Y, Z, and time coordinate, and this is going to be the one that is not going to be moving, and so that's going to be the one that always kind of says relative to Earth. And if we were to set one that was moving, and we're going to call that one S prime, so S prime is one that's going to be moving, and we set the origins at the same location at the same time is equal to 0, then what we can do is anything that's moving is going to get a prime, and if it was just moving in the positive x direction right here, then it would be pretty straightforward. We would say that we could just write x is equal to x prime plus whatever speed we have multiplied by time. The y's are actually going to be the same, and if we drew a z-axis it would also kind of be the same, but that's kind of omitted from the picture right over now. And we would also be able to say, well, we can write the speed in the x direction is going to be equal to the speed in the inertia or the moving reference frame multiplied by the time. Now, kind of the problem with this is we can kind of see that as the reference frame starts to move at or near the speed of light, then this is going to break down. So as we kind of said in the previous slide, the speed of light has got to be the same for both of these reference frames, and other things are going to start to dilate or change, and it turns out that time is going to start to change. So here's a fun little thought process on simultaneity, which is essentially how we can log events which happen in some time with some distances. And if we were to consider a train that is moving, so we're going to have a moving reference frame called S prime, and on this reference frame we're going to have Mavis, and outside of it in a non-moving frame we're going to have Stanley. And what Stanley observes is he sees lightning hit the front and the back of the train right over there, and he's kind of equidistant from these 2 points, A and B, and so he says that the flashes happen at the same exact time. Now, Mavis right here, she sees that Stanley is equidistant from A to B, and she agrees with Stanley on the time that it took. However, she believes that lightning did not hit the front and the back of the train simultaneously. What Mavis kind of observes is she's moving in this direction, and the front kind of coming off of B and the front coming off of A are going to travel like that, and she's moving towards the front that is traveling towards B, and so the one from B is going to reach her first, and she's going to think that lightning hit the front of the train before it hit the back of the train. So kind of the takeaway from this is both of these observers are correct in their measurement of time. However, they can disagree on the amount of time that it takes, and so time is going to be something that's going to start to dilate or change if we have moving observers. So let's take these two observers, Mavis and Stanley, just a little bit further. We know that they measured the time interval differently for the lightning, and so they actually also disagreed on whether the lightning was simultaneous or not. If we were to consider a case where we have Mavis inside of a moving reference frame, and there's going to be a source sitting right next to her, and that source is just going to be a laser or something like that, and it's going to send up a pulse of light. Then that pulse of light is going to go all the way up. It's going to bounce off of a mirror on the top of the train, then it's going to move all the way back down, and Mavis is going to measure some time interval, and that's just going to be the delta T naught. Keep in mind that she's in the moving reference frame, and here we have Stanley, who's in S, and what Stanley is going to observe is he's going to observe the light take this path where it's going to go up like this, and the path is going to come down just like this, and so he's going to measure a different time, and actually it's going to be a longer time, and that's going to be a delta T. Now, the book works you through the derivation of how we can relate their two time intervals, but I'll just kind of give it to you right over here, and I wrote it beforehand just to save on my messy handwriting. And essentially we can relate Stanley's time interval to Mavis's time interval divided by this guy right over here, and we actually see this guy right over here a whole awful lot. We're going to call that a gamma, which is going to be a fish on its nose, and that's just going to be 1 divided by the square root of the square root or 1 divided by the square root of this quantity right over here, where u is going to be the speed of the moving reference frame right over there. And so you could write this guy just like this. Now, a couple things to kind of keep in mind is this guy right over here is always going to be larger than 1. And if u is a small fraction of the speed of light, say 0.002 multiplied by c, then this gamma right over there is going to be very, very, very nearly 1. And so the time intervals are going to be close enough. We would call that non-relativistic. If we were to talk about what happens as u becomes much larger, say 20% of the speed of light, then all of a sudden this gamma factor right over there is going to start to matter, and the time delay will be more noticeable. We would call that relativistic. And the last thing I do want to point out is because gamma is always going to be larger than 1, then the time measured by Stanley, or the one that is not moving, is always going to be smaller, or is always going to be longer than the time measured by the moving observer. So this leads us to something that is called proper time, and if you were to think about it, we always want to deal with the more fundamental delta t naught, and that's going to be the time measured in the moving reference frame, because there is going to be infinitely many moving reference frames and only one reference frame that is not moving. So proper time is going to be measured in the moving reference frame. And so one thing to kind of keep in mind is that that's going to be the time interval between two events that occur at the same point. So you can kind of picture all of these clocks on this x, y, and even z coordinate system. And when we talk about proper time, we're kind of starting all of these clocks at the same exact time, and all of these guys are synchronized, and we're measuring the time difference relative to, say, this point in time. Now, this leads us to just kind of the wording in this chapter a little bit. A lot of times we're going to see things like so-and-so observes something happening at a certain amount of time, and that's going to be starting with synchronized clocks. It's not going to be, so-and-so sees this, because there is going to be a little bit of time it takes for the light to travel between two observers. So let's take a quick look at example 37.1 in the book, and that example tells us that a muon, which is going to be a high-energy subatomic particle, has a lifetime of 2.2 microseconds when it's at rest. And what's going to happen if we get this muon moving at 99% of the speed of light? Well, this 2.2 microseconds is going to be the lifetime of that muon in its own reference frame. So the only thing that's tricky is that's going to be the delta t naught, and it says, well, what time interval would someone on Earth measure? And that's going to be the delta t, and we're pretty much just going to say delta t is going to be equal to delta t naught divided by the square root of 1 minus u squared over c squared, and here u is equal to 0.99 c, and so we're going to have 2.2 microseconds divided by 1 minus 0.99 squared. We're just kind of left that c right there, and those c's cancel each other out, and it's going to be 15.6 microseconds. So much, much, much longer than the 2.2 microseconds, and this thing is going really, really, really fast. I'm not going to work this example, but you could convince yourself, looking at example 37.2, that when we're talking about airliner speeds, so we're taking a look at speeds that are maybe around 300 meters per second or so, that this gamma term is going to essentially be 1, and there will be virtually no time dilation. Now, because time kind of dilates, we can consider another thought experiment that we're going to call the twin paradox. And if we were to consider having two twins born at the same exact time here on Earth, and one of the twins hops onto a spaceship and travels really fast, say at or near the speed of light, then what she's going to observe is she's going to observe twin number 1 moving away from her at nearly the speed of light, while and she's going to think that time is going to slow down for twin number 1. Twin number 1, on the other hand, sees twin number 2 in the rocket ship and thinks that time is going to slow down for her. So when she turns around and comes back, they're each going to think that the other one is younger than she is, and that's essentially a paradox. That can't happen. Now, kind of what's going on right here is one of the twins is in a roughly inertial reference frame, and that's going to be twin number 1. Twin number 2 is in a non-inertial reference frame, and so if you analyze it kind of carefully, we would realize that twin number 2 has got to be the younger of the two twins. So now that we've talked about how time dilates, let's talk about how length can be affected. We're going to not talk about length dilation, we'll talk about length contraction. I didn't make the world, I just try to live in it. If we were to consider kind of the same setup before, where we had a laser that sends out a pulse, and we had a mirror right over here, then that laser pulse is going to go like that. It's going to come back, and we're going to have Mavis, who is moving, measured length, and we're going to call this the proper length, and that's because the source and Mavis are in the same reference frame, and so that's going to be the L0. If we had Stanley way out here and he's watching the same thing, then he's going to measure a length, and that length is actually going to be a little bit shorter, and so that's going to be this guy right over here. Kind of what's going on with that is we can always say that distance is going to be equal to rate times time, and we know that time is going to be shorter for Mavis than it is for Stanley, and so length has to kind of change correspondingly because the speed of light will be the same in both reference frames. And so just like we kind of multiplied time by gamma, length we're going to divide by gamma. And so we could say the length measured by Stanley is going to be equal to the length measured by Mavis divided by gamma, or with the U's and the C's just written like this. Now, one thing to keep in mind is if the lengths are perpendicular to the direction of motion, then there's not going to be any length contraction whatsoever. So only when we're measuring lengths like this will we measure a length contraction. And if we had a ruler standing kind of upright and Mavis measured it to be 1 meter, then Stanley is also going to be looking at it and he's going to see 1 meter. So that length contraction is only going to happen if it's laying in the same direction as the motion. So example 37.4, we have a spaceship that's moving at 0.99 times the speed of light, and someone on the spaceship measures the length to be 400 meters, and so that's going to be the L0. And we have some people on Earth. The question is what length do they actually measure? What they're going to actually see is they're going to see it look kind of squished, just like this, because it's moving really fast, and so we would expect it to be smaller. And so it's going to potentially be equal to the 400 meters multiplied by the square root of 1 minus u squared over c squared, which is going to be 0.99 squared. And when you type all that in, you're going to get 56.4 meters. So again, it's going to look kind of squished. Now, if we were to look at example 37.5, and we said, well, if we knew these two observers on Earth were 56.4 meters apart, how far apart would someone on the spaceship kind of perceive them to be? Much like they perceive the spaceship to be squished together, then someone on the spaceship is going to see these two guys appearing to be squished together. And so we have to be kind of careful here. The length that someone on the spaceship is going to measure is going to be the 56.4 meters multiplied by 1 minus 0.99 squared. And so someone on the spaceship is going to think that these guys are squished together, and they're going to be 7.96 meters apart. So this now leads us into the Lorentz transformations, which are very similar to the Galilean transformations, except that they're going to deal with relativity. And we're going to set it up the same exact way. We're going to have a frame S that is not moving, and we're going to have a frame S prime that is moving, and it's actually moving in the positive x direction with speed u. And some things we can kind of see right over here. The origins are going to line up at time is equal to 0 in both coordinate systems, and we're going to have these variables in S, and then all the primed variables in S prime. And something you can kind of see is that the y's are actually going to look the same, and the z's will actually look the same. We do know that the x's will be transformed, the speeds will be transformed, and the times will be transformed. So the book goes through all the gory details. I'm not going to bore you too much with that, but we can measure x prime. Again, that is in the moving inertial reference frame. As such, the y's and the z's will be unchanged, and time is going to start to dilate. More importantly, we're also going to be able to write the speeds, and this is going to be the speed you would measure in the moving reference frame relative to the non-moving reference frame, and the speed at which the reference frame is moving. And then this would be the speed you would measure in the non-moving reference frame if you were given the speed that was measured in the moving reference frame. And again, the reference frame is moving at a speed of u. So I know that sounded kind of complicated. Let's take a look at example 37.7, where we have a spacecraft that is moving at 0.9 c relative to Earth, and it fires out a space probe that is at 0.7 c relative to it. And what we're interested in is what speed would we measure if we were on Earth. So Earth is not moving, so it's not going to get the prime, and so we're going to use this guy right here, and we're essentially going to pretty much plug them all directly in, where this is going to be 0.7 multiplied by c plus 0.9 multiplied by c divided by 1 plus 0.7 times 0.9. Both of those multiplied by c, but because they're divided by c squared, they kind of cancel each other out, and we're going to get a speed of 0.982 multiplied by c. And we're happy and hunky-dory because we have a speed that is not faster than the speed of light. Now let's talk about example 37.8. Now Earth sends out a scout ship that moves at a speed of 0.95 c relative to Earth. What speed would the spaceship then perceive? Since the spaceship is moving, now we're looking for v prime, and so we're going to use this guy right over there. And it's going to be 0.95 multiplied by c minus 0.9 multiplied by c, that is the speed of the spaceship, divided by 1 minus 0.95 multiplied by 0.9, and so the spaceship will perceive a speed that is going to be 0.345 multiplied by c.